The question we're interested in as psychologists is how we perceive lightness and color. Vision of these properties begins when light reaches the eye reflecting off of objects. However, the light that gets into the eye isn't the property of the object itself, so what we need to understand is how the brain turns that absolute amount of light that gets into the eyes into a percept that's indicative of object properties. Why is this difficult? It's difficult because the amount of light that gets to our eye from different objects, say a white object in shade and a black object in the sun, can be quite different than the reflectance properties themselves. For example, a white object in the shade can actually reflect less total light to the eye than a black object in bright sunlight. And if the brain didn't have some sort of mechanisms that compensated for this and took the illumination into account, we might see the white objects turning from, say, black to white as they move from sun to shadow. What we want to make sense of is how the brain stabilizes our percepts of objects so that we don't see the same object changing color rapidly from one illumination to the other, say from white to black. If the brains didn't do that, vision would be not so useful for understanding the way objects look. Here we have a white block and a black block, white and black, and the black reflects less light to the eye than the white. These are on about the same amount of illumination. However, if I were to pick up this white block and move it into the shadow, the amount of light getting to the eye is reduced. It still looks white to us sitting here, but now the amount of light getting to your eye from the white block is probably less than the amount of your eye getting to that black block, yet the visual system is preserving the perceptual difference.
If we look at what white and black are physically, they vary in their molecular structure, and that determines how much light they reflect. So a white surface typically reflects about 90% of the light that strikes it, whereas a black surface reflects no more than about 3%. That's a range of about 30 to 1. That a white surface will reflect 30 times more light than a black under the same illumination. The problem is that in natural images, because there's variations of illumination in addition to variations of reflectance, you get a much larger range in most images that we see. It can easily be more than 10,000 to 1. It can be as high as 1,000,000 to 1. So how is the brain supposed to deal with this huge range? If, for example, it were to take the brightest thing in a scene and call that white, and then it went down the scale to something that's, say, 30 times darker than that and called that black, what's it supposed to do with all the values that are below that, a wide range of values that would fall off the scale?
One hypothesis is that the visual system segments the image into separate regions of illumination. Now, this would effectively reduce the range of light intensities that need to be mapped and allow the visual system to compute lightness based on ratios. In other words, the ratio of light intensities that reaches the eye from any two surfaces within a single field of illumination would be equal to their actual reflectance ratio. In order to test this hypothesis, we created images that, similarly to the real images, have a large range of light intensities, as large as 10,000 to 1, but do not contain cues that would allow the visual system to segment the image into separate fields of illumination.
Next, we asked observers to match a target, the center square on a checkerboard, to a shade on a scale that ranged from black to white. After the observers indicated their best match using the slider, the target changed colors, and we asked them to make another match. What we found is that observers were able to match a 5,000 to 1 ratio of light intensity to this reflectance range indicated by the slider box of only 100 to 1. And this falsifies the hypothesis that observers are only using ratios to determine lightness, even in these unsegmented images.